Hello guys, welcome to this video. In this video we will be continuing all our previous explorations about all the functions and developments that we did, and in this video we shall also find out more about the properties and all the different discoveries that we can make about this exact function and the distributions that we are studying. And meanwhile there would be a lot of solved problems as well, so just head forward to the video. We can start over from there. In this one we are going to look at the following problem. Well, obviously, after we look at the problem, we will see how to exactly make sure that we know all the necessary tools and fundamentals to understand this problem. After this part of the video, it will be included within the video. So whatever we are about to study here, or whatever we are about to solve here, the necessary tools that are required is already present in the next part of the video. So either what you can do is watch it first by skipping it ahead, and or you can just solve it first, and then if you want a revision you might actually check out the next part of the video as well, which is included in the same video. So what I'm going to discuss here is basically about the Taylor series representation. So what we usually do is we try to represent a function f of x in terms of an infinite series like a naught plus a1x plus a2x square and all the way. So this is called the Taylor representation or the Taylor polynomial for a series. So how do we actually find the coefficients? That's a question. Now if we were to express a function in terms of polynomial, like let's say any function, so that function might as well be approximated by something relating to the function itself, right? So these coefficients a0, a1, then a2 and stuff, these coefficients must be related to themselves, related to the function f, right? But how do we do that? So if you notice, this can be written as in summation notation n equals to 0 to infinity an x to the power n, right? Where an's are the coefficients and x is the variable belonging to some domain D, where D is the radius of convergence. What is D? D is basically the radius of convergence. So what we want to do is we want to find this coefficients an. There's a simple way for doing that. So first of all, if you look at this series and if you put in f of 0, what you do get is f of 0 equals to a naught, because you see that all the other terms become 0, right? So a naught is f of n, f of 0. Now how are we supposed to find f1? If you differentiate it one times, what you get is something like this: a1 plus 2a2x and so on, right? So considering the function is differentiable, if you now put it with the value 0, considering that f dash x is continued as 0, what we get is a1. So a1 is f dash 0. In a similar way, if you just look at the infinite series representation, if you differentiate the function n times, fn of x would just be summation n equals to 0 to infinity an into n factorial, and this would be x to the power 0, but there of course are more terms after that. So therefore the general coefficient should be an equals to fn 0 by n factorial for all n, and in all n we include the natural numbers and we also include the integers 0, because although we have already found the value for 0, but we still include it. So this is how we use the Taylor series and Maclaurin series, and how do we prove it? Well, you have seen it earlier, but now we are going to use it in the problems and the theory that we are going to study after this. So the related theory is also given with it, so if you'd like, you might also check that out after this one as well, because that was also helpful. evaluate integral of x cube into root over of x to the power 4 plus 2 dx. Right. So I'll give you again 10 seconds for you to solve it or have an idea of it, or if you want to solve it completely, please pause the video and take as much time as you can. Okay, so I hope you did solve the problem, or if you couldn't, you were stuck at some particular idea. If your idea actually was to substitute this term, it was correct, because we are going to do exactly that. What we are going to do is this. Let us denote, first we denote the integral by some variable capital I, which is x cube into root over x to the power 4 plus 2 dx, and we set y equals to x to the power 4 plus 2, because when we differentiate both sides, what we get is dy equals to 4x cube dx, right? And we want the value for x cube dx here in terms of y, so therefore x cube dx is just dy by 4, and then the integral becomes I equals to integral of, that thing becomes dy by 4, the x cube dx thing, and this becomes root over of y, right? So it's 1 by 4 into integral of root y dy. It's 1 by 4, and root y of dy is just y to the power 3 by 2 by 3 by 2 plus c, and this would be 2 by 3 into 4, which is basically 1 by 6. So the answer is 1 by 6 y to the power 3 by 2 plus c, and if you can substitute y back, the answer would become 1 by 6, and y was x to the power 4 by 2, so it's x to the power 4 plus 2 whole to the power 3 by 2 plus c, which is the answer for our integral. So this really are some of the easier integrals which we are trying to evaluate here, because it's just simple substitution and nothing much to find here. So we'll try to do some better problems. So let me introduce you to you the new concept, which is integration by parts rather, and then we can continue solving problems which are mixed from both the sections. So integral by part, which is also known as IBP in short. So as the name suggests, it is actually a rule to find out integrals of the form where you have two functions fx into gx dx. What we do here is we try to name or label the functions as function 1 or function 2, and once we do that, we can have an easier rule to find out the integral in terms of another integral, which might be easier to solve. So as of derivatives, it does not obviously give you a direct answer, but it rather gives you a newer integral which might be easier to solve, and we have a rule for it. The rule is something like this. The rule is called ILET. I for inverse functions, L for logarithmic functions, A for algebraic functions. Algebraic functions means function of polynomials like x cube, x to the power 4 plus 2 and something like that. Logarithmic is involving log, inverse is involving sine inverse x, cos inverse x, tan inverse x, like that. So they're inverse trigonometric functions. T is for only trigonometric, and E is for exponential. So why is this order important? This order is to choose the function that you choose is which is higher up the list, like which is like if the function, there are two functions in multiplication form, which is one of them are inverse and another one is algebraic, then you would have the inverse function as the first function and the algebraic as the second function. So if the function is higher up on the list, you would name it as function 1 and the other one would be function 2. So let us name here fx as function 1 and gx as function 2. Then what it gives you is function 1 directly comes out into integral of function 2 dx minus integral of derivative of function 1 into integral of function 2 dx multiplied by derivative of function 1 and the integration of this whole. So this is how it works. So you take the first function and you multiply it by the integral of the second, and you subtract from it integral of derivative of the first function into integral of the second function. So let us take some examples so as to understand how this works. Example 1. Let us find out the derivative of x log x dx. Okay. So identify x is an algebraic function, right? ln x is logarithmic. So which one is more up the list? Obviously L, right? So L should be treated as the first function and x should be treated as second function. So denote the integral by I. Integral by I, and what we do get here is I equals to integral of x log x dx. Given that log x, we are denoting log x as first function, x as second function, which means we should have first function into integral of second function minus integral of derivative of first function, which is just 1 by x, into integral of second function and the integral of the whole thing, right? So integral of x dx is just x square by 2, right? So it should be x square ln x by 2 minus, we have already found the derivative for log of x, which is 1 by x, and again integral of x is x square by 2. So in this inner integral you do not need to include the constant plus c, so we are basically trying to just find the integral and accept the constant. So 1 by x into x square by 2 dx, and as we can see this becomes x square ln x by 2 minus integral of this x is cut off, it's x by 2 dx, which can also be evaluated because x square log of x by 2 minus this is x square by 2, so this is x square by 4. Now we can include a plus c to complete our answer. So x log x could not be evaluated otherwise. The only way is to guess the function whose derivative is x log x, which is kind of impossible. So we do not really need to follow that strategy, obviously, but this would give us the answer, right? Okay. So let us try to find out some more problems. For the next problem, what we do need is this: d dx of tan inverse x is equals to 1 by 1 plus x square. We are going to prove it, but first understand that since the derivative of tan inverse x is 1 by 1 plus x square, this also means that integration of 1 by 1 plus x square is equals to tan inverse x plus c. Okay, and how do we prove it? Okay, so let y equals to tan inverse of x, then what we see is x should be equal to tan of y, right? And what we are trying to find is dy by dx, so let us see how to find that. And the derivative of tan y is sec square y, if you remember it from the derivative section. So differentiating both sides, we get dx equals to sec square y dy, and sec square y is just 1 plus tan square y dy, and so dy by dx would be equals to 1 by 1 plus tan square y but tan y is just x, so it is just 1 by 1 plus x square, right? So the derivative for tan inverse x, which is dy by dx, is 1 by 1 plus x square. Proving it, and all the other inverse functions can be proven in the same way, and corresponding to that we can find this integral. Evaluate integral of x to the power 4 by 1 plus x to the power 10 dx. Now at first glance, obviously that we want to eliminate the or substitute for the denominator, but we see that the derivative of 1 plus 1 x to the power 10 is not x to the power 4 dx, right? Or not any constant multiple of x to the power 4 dx rather. But what we can do here is denote the integral by I, then what we get is this: capital I is equals to integral of x to the power 4 dx divided by, and we can write x to the power 10 as x to the power 5 whole squared, because in that case what happens is, if we substitute y equals to x to the power 5, what we get is dy is equals to 5 into x to the power 4 dx, right? And what we want is the value of x to the power 4 dx, so therefore x to the power 4 dx should be equal to d of y by 5. So our integral becomes I equals to integral of, this thing becomes dy by 5, and the denominator just becomes 1 plus y square. So taking the constant outside, we get 1 by 5 dy plus 1 by y square. Now since we already know the derivative integral for 1 by 1 plus y square is tan inverse y, but if we hadn't known that, what we could have done is we can use trigonometrical substitutions in problems where we have something of the form 1 plus x square or 1 plus y square in the denominator or in the numerator. Because if you substitute, and remember, obviously you can make as many substitutions as you can. There is no rule of making only a single substitution for a single integral. As you can see, I am going to make a second substitution now. I am going to substitute for the substituted variable itself. So substitute y equals to tan theta, where theta is another variable. Then dy would be equals to sec square theta d theta, if you remember the derivative of tan theta, and sec square theta is just 1 plus tan square theta d theta. And as you know, 1 plus tan square theta is just 1 plus y square d theta. So therefore, taking this on the left hand side, we get dy by 1 plus y square equals to d theta. So this whole thing becomes d theta, right? So therefore I equals to integral of d theta by 5, and integral of d theta by 5 is just theta by 5 plus c. But theta, as you know, if y is tan theta, then theta would be tan inverse y. Then the answer would be tan inverse y by 5 plus c. But we also need to put back the value of y, which we substituted as x to the power 5. So the answer would be tan inverse x to the power 5 whole divided by 5 plus c, which is our answer, right? Okay, so this is another problem, and let us do another one. This one would be from the section of IBP. So obviously, whenever you're facing or you're in a situation where you're in exam or some problem solving session, you might not be given the topic, right? So you might have to figure out on your own how to do a certain problem of integration. If it's a definite integral, or even if it's an indefinite integral, you might have to substitute for something. You might have to do integration by parts. So there are various ways to do an integral, and you need to figure out which way works for you, which way actually solves the integral, because other ways might actually make you go round and round and come back to the same integrand again, right? So let us evaluate x sin x dx. And after that we'll do a more complicated version of this. So denote by I the integral, and whenever we see functions which are product of two different kinds of functions, we try to remember our eyelet rule, where we obviously know which one to take first function and which one to take second function. So in the eyelet rule, as you can see, eyelet, the algebraic function comes first after the trigonometric function. So algebraic function should be part 1, function 1, and the trigonometric one should be function 2, right? Then we have I equals to x into integral of sin x dx minus derivative of x, which is d dx of x, into integral of sin x dx, and whole thing is dx here, right? Now integral of sin x is minus cos x, so this is minus x cos x dx, minus x cos x, minus d dx of x is just 1, and integral of sin x is again minus cos x, right? Then as you can see, it simplifies considerably into minus x cos x, and this minus make it a plus, and 1 into cos x is cos x dx, and you do know the integral for cos x dx, which is just sin x, right? So the answer is x minus x cos x plus sin x plus c. So this integral is something which just comes back around its own, because the trigonometric functions, the sin x and cos x functions, generally they come back around its own when you integrate them enough number of times. So for example, they have a period of 4 on integration, so if you integrate sin x 4 times, you will actually get the same result. So let us try to find out something else here. Next problem would be integral of e to the power x sin x dx. Now this is a problem where you would know why the denote by integral I is of paramount importance. Okay, let's see. Denote the integral by I. Then what we have is I is equal to e to the power x sin x dx. Now if you remember in the rule eyelet, e, that is for exponential functions, that came last, so obviously e to the power x is going to be the second function here, and sin x is going to be the first function. So applying IBP, or applying integration by parts, what we have is this: I is equals to sin x into integral of e to the power x dx minus d dx of sin x into integral of e to the power x dx, right? So what we do get is integral of e to the power x is just e to the power x, so it becomes e to the power x sin x minus differentiation of sin x is cos x, so cos x into e to the power x dx. Now this is another integral, so again we apply the same integration by parts technique with cos x as the first function and e to the power x as the second function. Notice how we have to do integration by parts twice here, and we are doing it, as you will see why. It becomes cos of x into integration of e to the power x dx minus the integration of d dx of cos x, and as you know, integration of e to the power x dx is just e to the power x. I'll just write e to the power x dx here. So it becomes e to the power x sin x minus e to the power x cos x, and d dx of cos x is minus sin x, and minus becomes plus. It becomes e to the power x sin x dx. And if you take it away from the bracket, what becomes is e to the power x sin x minus e to the power x cos x minus integral of e to the power x sin x dx. But notice that this is the integral that we started with, right? So this is denoted by I, which is a variable. So this becomes e to the power x sin x minus e to the power x cos x minus I, and on the left hand side we have I. So solving for I, what we get, solving for I, we get 2i equals to e to the power x sin x minus e to the power x cos x. Therefore I is equal to e to the power x whole into sin x minus cos x by 2, which obviously there is a plus c, which is the answer. So this is one of those integrals where you have to do integration by parts twice to get the answer. So this is a problem where we have basically the integral coming back on its own, and then we have to solve it like that. So this happens a lot of times. So let us do another problem. This one would be a bit tad harder than the last one because of the concepts involved. Evaluate integral of sine of log x plus cos of log x dx, right? Now obviously what we want to do here is, first, as this is not any function that we can be reminded of, this is not any elementary function, neither does it have substitution that is very clearly visible. So obviously the derivative of log x is also not present, right? So naturally the first thing we would like to try is to substitute for log x and see if that makes any difference, right? So obviously I is equals to integration of sine of log x plus cosine of log x dx, and substitute y equals to log x, which will give us dy equals to 1 by x dx, right? Therefore this integral would become, and from this you can see that dx is basically equal to dy into x, but we need it in terms of y, so x is basically e to the power y, so dx is basically e to the power y dy, right? So the integral becomes sine of y plus cos of y whole into e to the power y dy. And this is time to introduce a new theorem, or rather a lemma, which is helpful sometimes. So lemma: for a differentiable function f of x, if I is equal to integral of e to the power x into f of x plus f dash x dx, then the integral is I equals to e to the power x into fx plus c. So if you have an integral in this form, the answer is simply e to the power x into f of x. So the proof is necessary, so we shall do the proof here. We start with the integral, given integral, and we shall see why this lemma is important in solving this problem, this particular problem. So given integral is I equals to e to the power x whole into f of x plus f dash x dx. Now let us separate it into two different parts, that is e to the power x into f of x dx plus e to the power x into f prime of x, or derivative of fx dx. So let us try to break down this second integral. Name this integral as b. So b equals to integral of e to the power x into f prime x dx. If you apply integration by parts here with e to the power x as the first function and f dash x as the second function, what you do get is e to the power x into f dash x dx minus derivative of e to the power x is just e to the power x and integral of f dash x and then a dx outside, right? Now we know that the integral of a derivative is just the function itself, so it just becomes e to the power x into f of x minus this becomes integral of e to the power x into f of x dx, right? So if we put the value of b there, we see that I is equals to integral of e to the power x f of x dx plus b, where b is our desired integral which we have just evaluated using integration by parts, and which becomes e to the power x into f of x dx plus e to the power x into f of x minus integral of e to the power x into f of x dx. And as you can see, these two integrals cut off because they are exactly the same thing, so the answer is just e to the power x into f of x, which is the answer for the integral. Now in our given problem, in our given problem we have I equals to integral of e to the power y, it was, into sine y plus cos y, right? So let f of y equals to sine of y, then f dashed y would be equals to cosine of y, and therefore I equals to e to the power y into f of y, which is sine of y, and cos y is the derivative, so f dashed y, right? And from the lemma we see that this is basically equals to e to the power y into f of y plus c. Putting back y, we get e to the power, and what was y again? Y was log of x, right? So we get e to the power ln x into f of ln x plus c. Now e to the power ln x is just x and f of ln x is just sine of ln x plus c, which is the answer to our integral. So you see that this integral is found out using this law, and we can easily find out different integrals as well using this kind of lemmas whenever they're in the form of e to the power y into f of y plus f dashed y. Okay, so this makes x plus 4 whole cube by 4 plus c, and these are the two ways that we can evaluate this integral, right? Okay, so let us move on to another example which would be a little bit more trickier, or maybe a bit tad harder than this one. Let us evaluate sine of ax plus b for real numbers a and b. Okay, for real numbers a and b. Okay, so how do we do that? Well, obviously in that case also what we are trying to do is we are trying to substitute this thing ax plus b, because were it only sin x dx it would have been easier, right? So let us name the integral as I, and let us substitute y equals to ax plus b. Now as in the previous problem, what we are going to do is we are trying to differentiate both sides to find an expression for dy in terms of dx, right? So differentiating both sides, we get dy is equals to a into dx, because the constant b would disappear and a into x's into differentiation is just a, and we have an extra dx always, we, as I told you. So dy would be a dx, or in other words dx should be equal to dy by a. Okay, now this would turn our integration something like this. It would be sine of y, because ax plus b is y, and dx would be dy by a, and this would give you 1 by a sine y dy. Now we know the integration for sine y, it is just minus cos y, so the answer would be minus cos y by a plus c. And it's time to put back the variable which we substituted, which would give us cosine of ax plus b by a plus c, which is the answer for our integration. So as you see, like this kind of equations are this kind of integrals can be solved by using simple substitutions, but obviously there are harder ones. So let us try to find out another integral. Evaluate integral of 1 by 1 minus 2x dx. Now what does this resemble of? Firstly, because the simplest way we can evaluate an integral or to find out what to substitute is to find out the most recent or the closest integral which it resembles to. So as far as I can tell, this resembles to something like this, right, whose integral we known as ln of x. So if we can somehow transform it in this form, that 1 by some variable and d of that variable, we can do that. An obvious way to do this is to substitute 1 minus 2x, and since it is linear, we substitute y equals to 1 minus 2x. Now y equals to 1 minus 2x would give us a pretty easy way to evaluate this integral, because when you differentiate both sides, what you get is dy equals to minus 2 dx, right? And this would give you dx equals to minus dy by 2. Using this I should be equal to 1 by 1 minus 2x is just 1 by y, and dx is just minus dy by 2, right? And so the constant minus 1 by 2 comes out, and we have 1 by y dy. Now this would give us minus 1 by 2 ln of y plus c, and it's time to put back what we have substituted, which gives us minus 1 by 2 ln of 1 minus 2x plus c. So you understand that we are in every problem, what we are trying to do is we are trying to reduce the integral by using some magical substitution, or rather a rational one once you try to get the hang of it, to reduce it to an elementary integral we know of, and then evaluate it directly, and then put back the value of the variable once it is out of the integration to get back our result. So this is what we call the method of substitution. We'll see a lot more examples in the coming sections, obviously. So the general version for this one would be, the general version for this type of integral is dx by ax plus b, and you can evaluate it. So let us name it as I. Substitute y equals to ax plus b. Now when we substitute y equals to ax plus b, we can have dy equals to a into dx, right? Then I should be equal to integral of dx is dy by a, so put a 1 by a outside, dy here, and this should be y. So this would give you 1 by a ln of y plus c, and if you put back the value, it would give you 1 by a ln of ax plus b plus c, which is the answer. Okay, now next example what we can get is something like this. We can try and find out some of the basic theorems regarding this, like so this one is a tad harder, but What I'm going to teach you in this, in regard to this problem, would be something that you should remember in your way along. So this type of an integral is not something where you just magically find the substitution, but rather you literally look for something. So that something is determined by the following theorem. Theorem says that if you have f of gx into g prime x dx, this is the form of the integral, which as you can see is the chain rule. Then this is equal, then this is basically equal to the integral of f of gx d of gx, or you can say this is equal to f of y dy, where y equals to gx. So you just need to integrate the function f. If the function f is integrable to you in an elementary form, you would be done, right? Okay. So what we are trying to find is, if we can find something, some function which is a function of something, and the derivative of that function is already given along with dx, we can directly substitute that function. Why? We can see why. So given integral is I equals to 2x into root over of 1 plus x square dx, and we can substitute y equals to 1 plus x square. Why are we doing that? Because see, I realize that the integral of 2x into root over 1 plus x square can be solved if we were to eliminate this root over 1 plus x square thing. So when I substituted y equals to 1 plus x square, I saw that the derivative of 1 plus x square is just 2x, which is given along with dx. So 2x dx would be substituted into a single dy, which is what we wanted, which is basically the form of this function, right? So the derivative of 1 plus x square is already given outside. So when we do dy, what we get is 2x dx, and that is helpful because this turns into root over y into dy, where 1 plus x square got to y and 2x dx was written as dy. And this is an easy one because this is just y to the power half dy, and using the rule you can find it as y to the power half plus 1 divided by half plus 1 plus c, which is basically y to the power 3 by 2 into 2 by 3 plus c, which is the answer, right? So this is the integral and this is the answer, and we can just substitute back to get our answer in terms of x, obviously. So it is basically 2 into 1 plus x square to the power 3 by 2 whole by 3 plus c. This is our integral, right? So this type of integrals can be solved, but you need to be a bit cautious about them. So let us do another one. Evaluate dx. So we want to evaluate 4x by root over of 2x square plus 1 dx. Again, it should be noted that ddx of 2x square plus 1 is equals to ddx of 2x square plus ddx of 1, right? And ddx of 2x square is just 2 into 2x, and ddx of 1 is 0, which gives you 4x. So you see that 4x is already present. The derivative of the term of 2x square plus 1 is already present. And if that is so, what we can do is we can substitute y equals to 2x square plus 1, and thus we see that dy is equals to 4x dx, and this would turn our integral into something like this. But this just only means that it's y to the power minus half dy, and using the rule we can write it as minus half plus 1 by minus half plus 1 plus c, which is basically y to the power half, and this becomes 2 because it's a half in the denominator. And we can substitute back our answer to find it's just 2 into root over 2x square plus 1 plus c. If you differentiate this using the chain rule, you would find that the answer is basically 4x in divided by root over 2x square plus 1, which is amazing because differentiating something is very easy while integrating something is insanely hard, just because of the methods or the ways you have to look for, right? Okay, let's do another one. Evaluate sine of root x by root x dx. Now again in this one, as you can see, the only portion that is not going with the integral is the root x inside the sine, right? And we are kind of sure that whatever else is present in the integral should be the derivative of that, right? So let's see. We observe d dx of root x is just equal to d dx of x to the power 1 by 2. Now we have learned previously that the d dx of x to the power something is just the coefficient comes out, so the coefficient comes out and the coefficient the power comes out as a coefficient and the power is reduced by 1, which means it is half into x to the power minus half, or in other words 1 by 2 root x, right? So if we were to differentiate, what we would get is something like this. Let y equals to root x, then dy should be equals to dx by 2 root x, right? But we see dx by root x is also present, so what we get from this equation is dx by root x should be equals to 2 dy, and we can absolutely put this to get the integral as I equals to sine of y, because root x is y, into 2 dy. Since 2 is a constant and is in multiplication with the rest of the integral, it comes out and we only have to integrate sine y dy, which is just minus cos y, so it's minus 2 cos y plus c, and putting the value of y back, what we get is minus 2 cosine of root x plus c. This is the answer, right? So you see, like, this kind of integrals can be solved, but then again we have to be a bit cautious. So let us solve a lot more problems. Example 7. I will try to do this as much as I can so that you get the idea of method of substitution completely. And if you have any trouble in evaluating derivatives, please go back to the last videos to find out how to evaluate a certain derivative or how to do complex derivatives as well. Okay, so example 7, evaluate integral of 2x e to the power x square minus 5 dx. So let us denote the integral by I, so that I is equals to 2x into e to the power x square minus 5 dx. Note that now again in this integral we are trying to see that since the derivative of x square minus 5 is just 2x, what we can do is y equals to x square minus 5, which should give us dy is equals to 2x dx, right? Then on substituting, I is equal to e to the power y and the 2x dx becomes dy, right? And you know the integration of e to the power y is just e to the power y plus c, and you put in the value which was x square minus 5 plus c. So this type of integrals, if you find the derivative of a term directly present inside the integral, try to substitute for that term so that you can reduce it into a common integral or an integral that you know of, okay? Because only then would it be easier for you to find out what to do. So we will continue our examples, but first let us learn one more thing. Let us do one more example, then from the next one From the next video we shall also do all the other indefinite integrals that we are required to do in the method of substitution, but also we will do some of the definite integrals, and we will learn how to do the definite integrals as well. So let us do this. This would be example 8, right? Yeah. So we'll continue from example 9 in the next video. So this would be the last example for this video. So let us do this problem where we have integral of cosine of x dx by 1 plus sine x. So this one looks a bit more tedious than before, but note that ddx of sine x is just cos x, right? So as we can see, cos x dx is present in the numerator and 1 plus sine x is in the denominator. So if derivative of sine x is cos x, then derivative of 1 plus sine x should also be cos x, right? So rather than going for the substitution y equals to sine x, what we can do is we can directly go for the substitution 1 plus sine x, then let y equals to 1 plus sine x, and from that we get dy is equals to cosine of x dx. This would give us our integral as y equals to integral of dy divided by y, which is just the integral. This integral is evaluated as a natural logarithm, right? So ln of y plus c, and remember the y is always positive, so it's rather a modulus. So the answer by putting back the value of y would be ln of 1 plus sine x plus c, which is the answer. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.